We're going to take a look at Chapter 13, which introduces the logic of hypothesis testing. So first of all, what is hypothesis testing? Hypothesis testing is using data from a sample to decide how strongly it supports a research hypothesis. It's used to determine whether the observed result from the sample is statistically significant. The first step in hypothesis testing is to formulate the hypotheses to be tested, and the hypotheses are based on the research question. They should be formulated at the design stage of your study before your data is collected. The example we're going to use today, and granted, this is not hypotheses that were designed before the data were collected, but we're working with data that already exists, not performing a new study. So we're going to use the Galton data, and we're going to consider this research question. Today, the mean height among adult males living in England is 69 inches. In the late 19th century England, was the mean height among adult males different than it is today? Now, the first hypothesis that we're going to formulate is called the null hypothesis. We use the notation H with a 0 subscript to denote it, and it is the statement that we seek evidence to disprove or nullify. So this is going to be that the answer to the research question is no. So in our situation, where we want to know in late 19th century England, was the mean height among adult males different than today? The answer no would be that it's the same, and so that's going to be our null hypothesis. The null hypothesis is that in late 19th century England, the mean height among adult males was the same as today, which would mean that it was equal to 69 inches. The other hypothesis that we formulate is the statement that we seek evidence to support. That is, that the answer to the research question is yes. So in our situation, that would be an alternative hypothesis that in the late 19th century England, the mean height differed from today. The mean was not equal to 69 inches. Now, the next step we're going to take in hypothesis testing is to identify a test statistic. This is a number that's used to summarize the data in the sample and summarize it in a way that's helpful for trying to address the research question. So depending on the situation, this could be a sample mean or a model coefficient or some other number, and we're going to see lots of examples in the chapters that come. For our example, since our hypotheses are about the mean height among adult males in 19th century England, and Galton's data was a sample from that group, it makes sense that we might try using a test statistic as the sample mean in the Galton data. And the mean height among the males in the Galton data was 69.23 inches tall. The next thing we do with hypothesis testing, we're going to start thinking about how consistent the sample data are with the hypothesis that we want to nullify, the null hypothesis. So in order to think about this, we're going to need to figure out a probability distribution of the test statistic, assuming that the null hypothesis is true. There are two different approaches we could use to do this. One is to use probability theory in math. This is the sort of traditional approach. The other approach, approach 2, is to use computer simulations. This is a more modern approach. It wasn't available before there were computers that were fast enough to do this kind of thing, but now it's becoming more and more popular way of modeling probability distributions for our test statistics. So we'll apply these approaches to our situation. We're interested in the distribution of the sample mean if the null hypothesis is true. Remember that the null hypothesis is that the mean is equal to 69 inches. And we know that as long as our sample size is large enough, and in this case it is, I think there are 534 or something like that, and we'll see in a minute, was the sample size of the males in the Galton data set. So we do have a large sample size, which means the distribution of the sample mean is approximately normal, and the mean of that sampling distribution is at the population mean, which, if the null hypothesis is true, is 69 inches. And the standard error, or the standard deviation of the sample mean, would be given by the population standard deviation, sigma, divided by the square root of n, sample size. Now, because we don't actually know what the population standard deviation was in late 19th century England, we don't know what the standard deviation of males' heights was. We're going to have to approximate that with the sample standard deviation. And remember that we saw last week that if we take the sample mean, subtract off the population mean, which, assuming that the null hypothesis is true, is 69, and divide by s over the square root of n, where s is the sample standard deviation, that will have a t-distribution with n-1 degrees of freedom. So we have a way we can model the distribution of x bar using our theory. Now, the other approach we have is using simulation. So I'm going to assume that the null hypothesis is true. And remember, that would mean that the mean is equal to 69 inches, and that the amount of variability in the sample is typical of the variability in the population. Then I can simulate a distribution of sample means, and I'll show you the R code that I'm using to do this. So first of all, I'm looking to see in the data set of all males what the mean is. Right here, the mean is approximately 69.23. is the mean height among the males in the data set. And then here is the standard deviation among the males in the Galton data set. Now, what I did is I created a new object called null height. And what I did is I took the height from the males data set as a vector, and I subtracted 0.23, which was the difference between the mean in the Galton data set and our hypothesized mean from each of the values. And by doing this, I got a mean of this null height value of, almost exactly 69 inches, with a very tiny bit of rounding. Standard deviation, because I subtracted a constant from each of the values, is the same as it was in the original data set. Right? And I'm just kind of showing that this is the same as the standard deviation of height. So now what I'm doing is I'm just resampling the null heights, taking the mean of each resample and repeating that 5,000 times. You can see that what I get is I get a distribution of sample means from each of the trials. That's what we have over here. We're looking at the sample mean from each trial. That is approximately bell-shaped and has its mean right around 69 inches. And I calculated the mean of my trials here just to ensure myself that I am simulating results centered around the null value of 69 inches. So that's one approach you could take to simulating this distribution, assuming that the null hypothesis is true. The next thing we're going to want to do is we're going to find the p-value. And the p-value is a way of measuring how consistent our sample data are with the null hypothesis. And technically speaking, what it measures is it measures the chance of observing the sample statistic, our test statistic that we picked out, or one that's more supportive of the alternative if the null hypothesis were true. And so what this means is that if I have a very small p-value, it's telling me if the null hypothesis were true, I probably wouldn't have seen data like this. On the other hand, if I have a large p-value, it's telling me, this data is not that surprising if the null hypothesis were true. So as we're looking at sort of how strong the evidence is, if we think about it on sort of shades of gray kind of scale here, the thing to remember is that larger p-values give weaker evidence against the null. Smaller values give stronger evidence against the null. And, we can think about what's sort of, if it's below 1%, we say it's very strong. If it's above 0.1, 10%, we say it's weak. 5% is considered kind of moderate, and so on. So I'm going to think for a minute about what values are more supportive of the alternative hypothesis than the test statistic. In our example, the alternative hypothesis is that the mean's not equal to 69 inches. Our test statistic is a sample mean of 69.23 inches. And so statistics that are farther away from 69 than 69.23 than our test statistic would be more supportive of the alternative than that test statistic. And so the values that are farther away from 69 than 69.23 is are the values that are more than 69.23, and the values that are less than 69 minus 0.23, which would be 68.77. So the p-value is the chance that the sample mean is more than 69.23 or less than 69.77. So now I can go back and use the probability models that I derived to try to find these p-values. So approach 1 using the t-distribution. The p-value is the chance that the sample mean is more than 69.23 or less than 68.77. Doing some algebra here. I'm subtracting the hypothesized mean and dividing by the standard error on both sides of this equation. Once I do this, I know that this quantity has a t-distribution. And so this is the same as the probability that the t-distribution with n-1 degrees of freedom takes a value of 1.866 or more, plus the probability that it takes a value of negative 1.866 or less. Because our t-distribution is symmetric around 0, if I look at the area above 1.886 and the area below negative 1.886, these two areas should be equal. And so I can simply calculate the probability in one of these tails, either one, and multiply it by 2 to get the p-value. So here the p-value is approximately 0.0599, which, if you remember, it's around 0.05, so it's in that sort of moderate evidence against the null hypothesis range. Using approach 2. Now remember, with approach 2, I'm using this simulated distribution, and my p-value is the probability that my sample mean is more than 69.23 plus the probability that my sample mean is less than 68.77. So I use the tally function to count how many of the means calculated for my different trials were above 68.23. That was 151 over 5,000 total trials. And the proportion that were less than 68.77, that's 165 out of 5,000 total trials. I add those two proportions together and I get my p-value, which is about 0.06. Very similar to what I got using the approach 1. And again, this is moderate evidence against the null hypothesis. Now with formal hypothesis testing, once we've calculated our p-value, we often will compare the p-value to a significance level to determine if the results are statistically significant. Now remember that smaller p-values give stronger evidence against the null hypothesis, and larger ones give weak evidence against the null hypothesis. Significance level is something that's set by the researcher before the data are collected. Usually it's 5%. And it's the threshold that's used to determine whether the data are considered strong enough to be statistically significant evidence against the null hypothesis. So if we have a situation where the p-value is less than this threshold that we create, then we say we reject the null hypothesis. If the p-value is greater than the level that we select, then we say the evidence is too weak and we fail to reject the null hypothesis. So rejecting the null hypothesis is something we do when the p-value is less than the significance level. When we reject the null hypothesis, it means that the sample gives statistically significant evidence in support of the alternative hypothesis. Failing to reject the null hypothesis happens when our p-value is greater than or equal to our significance level. And in this case, we would fail to reject the null hypothesis, and there is not statistically significant evidence that the alternative hypothesis is true. It's important to remember that based on sample data, we can never say that in the population the null hypothesis is definitely true. We can only say that it's plausible. And because it's plausible, we're not rejecting it in favor of the alternative. So it's very important to remember, when you don't reject the null hypothesis, it does not mean that you've shown it to be true. In our example, we're testing at a 5% level of significance. Our p-value is 0.06, which is just a little bit too big for us to reject the null hypothesis. So we failed to reject the null hypothesis. Based on Galton's data, there is not statistically significant evidence that the mean height among adult males in late 19th century England differed from today. In the second video, we will take a look at the types of errors that we can make in hypothesis testing and how to calculate something called the power of a test. Thanks. Have a good day.